Okay. Earlier you've seen that if you assume a reactant is a limiting reactant, then you can verify if in fact it is, and if it is, then you can calculate how much of the other reactant you have left unused at the end of the reaction and how much theoretical yield would be. Now, here's a general strategy you can use for solving limiting reactant problems. You can assume one reactant is the limiting reactant and then just calculate the moles of reaction if it is completely used up. And then you do the same thing for the other reactant. Okay, you don't do any further calculations just yet. Based on these two results, you can figure out what the limiting reactant is right away. That's the one that would give you the smaller moles of reaction. Okay, if completely used up, because by the time you get the smaller amount moles of reaction, then you know that one reactant is gone, and so your reaction has to stop. Okay, so now that you figured out your limiting reactant, so these first three steps allows you to determine the limiting reactant, then you can just use the moles of limiting reactant as the basis for calculating the theoretical yield and your unreacted excess reactant. Let's illustrate that using this problem right here, using an ice table. Okay, so let's say you have a reaction 3H2 plus N2 yields 2NH3. Let's say you were to mix zero point 0.6 moles of H2 and 1 mole of N2. So here in our row for initial moles, we have 0.6 moles of H2, 1 mole of N2, and no NH3 to begin with. Okay? Then you determine the limiting reactant, the theoretical yield amount of unreacted excess reactant if the reaction were to go to completion. Let's see what happens here. Changes in moles according to the balance equation would be 3x, okay, for hydrogen, 1x for nitrogen, so you're going to lose x moles of nitrogen by the time one of the limiting reactants is consumed, and you're going to lose 2x moles, you're going to make 2x moles of ammonia. So at the end, you're going to end up with, oops, sorry, this should not be 1, that should be 0.600 minus 3x moles of hydrogen. You're going to have 1.000 minus x moles of nitrogen, and you're going to have 2x moles of NH3. The question is, what's our x going to be? Well, what if X is if hydrogen is the limiting reactant? Let's make that assumption. Then our X is going to be 1. Then we're going to say then our ending moles of H2 is going to be 0, right? So this will be 0. We lose all of it, right? So 0.600 minus 3x equals 0, or you can say 3x is 0.600. Like all 0.6 are gone, so the extent of reaction would be, that would be equal to 3 times the extent of reaction. So extent of reaction, divide both sides by 3, is going to be 0.200. Okay? What if the nitrogen is the limiting reactant? If N2 is the limiting reactant, then you can say X equals that all of that 1 will be gone, right? So 1.00 minus X is going to be 0. Okay, you can say 1.000 minus X is going to be 0. It will be used up completely. And then X would be equal to 1.000. So which assumption is valid? H2 will run out first. By the time the extent of reaction is 0.2, okay, then your H2 is gone. You can't get any more than that. So you can't achieve an extent of reaction higher than 0.2. So your nitrogen is not going to be used up. So this assumption then we say is the wrong assumption, that nitrogen is limiting. So you base your calculation on H2, the limiting reactant. So now you just have, you can easily figure out the answers. You can say the amount of H2, okay, left if you have complete reaction, If you have a complete reaction, then H2 would be 0 at the end. Your N2 would be 1.000 minus x, right? 1.00 minus x. And you know that x is going to be 0.2, so 1.000 minus 0.200, there's your x right there, would be 0.800. And the amount of ammonia you're going to have is going to be 0 plus 2x, so that's 0 plus 2 times 0.200. This is moles, by the way. It's going to be equal to 0.400 moles. Okay? And this is the amount of ammonia you're going to produce, so that is your theoretical yield. Okay? So that's how you solve that problem.